In this video, we're going to be talking about lines and planes. And the first subtopic we're going to look at is the idea of lines in R2. So let's define the general form of a line in R2. And we'll say that is an equation that has the form ax plus by equals c. For example, let's say someone gives us the line L, which has equation 3x plus y equal 1 in R2. So this equation that's highlighted here, that's in general form. And for example, one thing we might do is want to graph this line. So if we wanted to graph the line, we would choose any x value that we like. Let's say x equals 0. We would plug that into the highlighted equation and then figure out the y value that goes with that. So if we sub x equals 0 into this, we'd get y equal 1. And then that gives us the ordered pair 0, 1. So we might call that point P, for example. P is 0, 1. Similarly, you could choose any other x value, like say x equal 1, sub that into the highlighted equation. So now that equation reads 3 plus y equals 1, and you could solve for y that way. So the y value would be -2, and that gives us a second point, which we might call Q. So Q has coordinates 1, -2. And then once we've got those 2 points, then we could graph the line. So you can see the x and y axes here in the picture. Here's our point P at 0, 1, and here's our point Q at 1, -2. And so that gives us just a quick way of drawing the line. Let's define the normal vector. So in symbols, we're going to write little n for our normal vector. Normal vector is orthogonal to a line, and its components are the coefficients from the general form. So let's think about this in the context of the example that we just did. The line that we graphed at the top of the screen had general form 3x plus y equal 1. So if you grab just the coefficients from that line, you're getting 3 and 1. If you put those into a vector, you get the vector 3, 1, and we're saying that's our normal vector. So to build the normal vector, just grab the coefficients from the general form. Okay, and then what does that do geometrically? Well, it's orthogonal to our line, or you could say perpendicular to our line. So we graphed the line a little bit earlier. It had that sort of a shape. And the normal vector, if you think of a vector that's going 3 units horizontally, 1 unit vertically, would have about that direction there. And just by eyeballing that, you can say, yep, looks like the normal vector would be perpendicular to the line. So now we know what a normal vector to a line is. It's a vector that's perpendicular to our line, and we know how to find it. Its components just come from the coefficients of the general form. With that, we can define the normal form of a line in R2. So the equation that we're going to be thinking about is n dot x equals n dot p, where this vector n is our normal vector. Vector x just represents a vector of variables, so just the vector xy. And vector p corresponds to any point on the line. So what that means, grab any point on the line and just turn it into a vector. So you could say vector p is the vectorization of any point on the line. So let's find the normal form of the line 3x plus y equal 1 in R2. We're going to need 3 things. We need our normal vector. So just grab the coefficients from the general form, put them in order, and that forms your normal vector. Vector x is just a vector that contains your variables, so x, y. And then vector p is going to be the vectorization of any point on the line. So think about finding any point that satisfies this equation here. So you could choose, for example, 0, 1. You could choose, for example, 1, -2. You can make any choice that you like as long as your point is on the line. So I think just for simplicity, I'm going to choose 0, 1. And then vector p is just the vectorization of that point. So meaning just turn that point into a vector object without actually changing the numbers. Okay, and then from there, we can write down our normal form. So the equation for normal form is you go n dot x equals n dot p, where this dot here represents the dot product. So our answer would look like 3, 1 dot xy equals 3, 1 dot 0, 1. So that's the answer we're looking for. That's the normal form of that line that we started with. Now, just as an aside, you might be curious what happens if you actually expand here. So meaning if we calculate the dot product on the left side, we'd multiply the first components together. So we'd have 3 times x. We'd multiply the second components together. So you'd have 1 times y, which is y. Add those together. So we'd have 3x plus y equals, and then on the right side, our dot product equals 1. So this gives us our general form. So what we're seeing is that there's a deep connection between normal form and general form. It's easy to move from normal form to general form. You're just expanding the dot product. And it's also reasonably easy to move from general form to normal form. You can pick out the normal vector, and with a little bit of thinking, you can find a vectorization of a point on that line. So these are two ways of describing a line in R2. We've got our normal form, and we've got our general form, and we're going to work towards 2 more forms for a line in R2. So let's define a direction vector for a line. A direction vector is going to be written as vector little d, and what it is, it's the vector that goes from P to Q, where P and Q are any 2 points on the line. So just to draw a picture here, imagine someone gives you a line. You would find a couple of points on that line. Just call them P and Q. Build your vector that's running from P to Q, and that's your direction vector. So it's giving you a sense of what direction your line is moving in. The vector form of a line in R2 looks like this. It's an equation that reads vector x equals vector p plus t times vector d, where t represents any real number. So geometrically, what this is saying is that if you want to represent a certain line, let's call it L, we would need to know a point on that line. So let's say we know a point P on that line, and let's say we know our direction vector D is going like this. What this highlighted equation is saying is that if you want to trace out all the different points on this line, then you want to start at the point P, and you want to travel all different multiples along your direction vector. So if you go 0 multiples along your direction vector, you'd just be at P. If you go halfway along your direction vector, you'd get this far. So that would give you that point. If you go a full multiple along your direction vector, you get to this point here. Bigger multiples of D would take you to points out here, or you could go negative multiples of D. That would take you over in this direction. So by varying this number T, what you're doing is you're able to trace out all the different points on this line. So we're going to find the vector form for the line 3x plus y equal 1 in R2. Same line as we've been looking at through our previous examples. So let's think about what we need for vector form. I might write the vector form over on the side here just to keep us focused on what we're looking for. So vector x just represents a vector that contains variables. Vector p here represents the vectorization of any point on the line. So choose your favorite point on this line. I would say, let's say our point P, set x equals 0, solve for y. We get the point 0, 1, and we're just going to vectorize that. So meaning turn it into a vector so that we can create an equation that just involves vectors. Okay, t here represents any real number, so we don't need to do anything with that. And d represents a direction vector for our line. Okay, so what we need now is a second point on the line. So choose your favorite x value, let's say x equal 1, sub that into our general form here, and just solve for y. So that would force y to be -2. Okay, now that we've got 2 points on the line, we can build this little direction vector d by just looking at the vector that runs from P to Q. So think Q minus P, and we'd have 1, -3. So I'll just draw a picture to go with this. We're finding any point P on the line to use as our starting point. We're choosing a second point on that line to build a direction vector between the two. Okay, so now we've got all the ingredients and we can just write out our vector form. So the equation for vector form, vector x equals vector p plus t times vector d, and we'll just plug in all the details. So specifically for this line, it would look like vector xy equals vector 0, 1 plus t times vector 1, negative 3. And that's our answer. That's our vector form for this line. So we could say as t varies, the line is traced out. If we were to make a careful sketch here, the line would be oriented this way. So imagine you take the t value 0, then the equation collapses to xy equals 0, 1. And that's just describing a certain point on the line. So let's say that's this point right here. So that's what we're getting at t equals 0. At t equal 1, your equation becomes xy equals 1, negative 2. So that's actually describing the point Q. Let's say that's over here. And as you let t run through all possible real numbers, you're just going to be tracing out different points on the line. So t equal 2 would be here. You can have negative t values, like t equal negative 0.5 would correspond to that point there. And you're just going to be tracing out all the different points on that line as you run through all the different real numbers t. So this is why it doesn't really matter what choice of point you make. That would just shift your starting point to a different point on the line. But let's say you chose Q as your starting point, then as you run through all real numbers t, you are still going to trace out all the different points on this line. Now let's talk about the parametric form of a line in R2. What that is a set of two equations. And the way that you get parametric form is just by expanding the vector form. So let's run through an example quickly. So suppose you take the vector form that we had in our very last example. You could look at that last vector and you could just multiply the t into it. So that vector becomes t negative 3t. And then on the right side, you could just add those vectors together. So you could get t 1 minus 3t. So now your equation looks like xy equals t minus 3t. And if you just break that up into a set of two equations, just going component by component, first equation would read x equal t, second component would read y equals 1 minus 3t. That's your parametric form. So the idea is that it's easy to move from vector form to parametric form. You're just expanding that vector equation. And it's also easy to move from parametric back to vector. You're just condensing it back into vector form. So vector form and parametric form are very closely related. So in discussing these forms, we should point out that the forms are not unique. For example, if one person says, okay, I'm describing the line 3x plus y equal 1, so that's in general form, and someone else is talking about a line and says, oh, my general form looks like 6x plus 2y equal 2, those are the same line, because of course we can take the second line and divide both sides by 2 just to get the first equation. So when you talk about finding the general form of a line, there's not one right answer. There would be multiple correct answers that all describe that same line. So let's look at a summary, because at this point we've seen 4 forms for lines in R2. And the reason why we need the different ways is because different forms are useful for different geometry problems. So as we move through this section and as we move through the course, we're going to be solving a variety of different geometry problems. And so we want to have the flexibility of using the form that is appropriate for the problem. So let's just do a quick summary here of the 4 forms that we saw. First one we saw was general form, and we saw that was closely related to normal form. So let's just talk about those two first and make a connection between them. So general form, probably the one that feels most familiar. It's just where you've got your variables on the left side, some constant on the right side. And if you rewrite that as n.x equals n.p, then you've put it into normal form. So easy to move between general and normal form. Now a quite different form is vector form. So vector form is where you describe all your points on the line by saying start at some point on the line and then go varying multiples along your direction vector. So that's a very geometric way of thinking about a line. And from vector form, you can easily move into parametric form. So vector and parametric, very closely related. Parametric just breaks the equation down into individual components. And so you can move into parametric or into vector quickly once you've got one of those two forms. So that's all we need to know about lines in R2, and we're now going to talk about lines in R3. This should go pretty quickly because it's going to build on what we just discussed. So let's find the vector and parametric forms of the line in R3 through these 2 points. So let's start with thinking about what vector form looks like. It's going to be the exact same equation as we wrote down for a line in R2. So the conceptual idea is still that you've got vector x equals vector p plus t times vector d. And geometrically what you're saying is you can start with any point p on your line. You can build a direction vector for the line by looking at the vector that runs between p and q. And then by starting at p and going differing multiples along your direction vector, you're just tracing out all the points on the line. I would start with building the direction vector. So direction vector d is just the vector that runs from p to q. So think q minus p. That's going to look like -2, -4, -6, and then we can fill in our vector form. Now, when we were in R2, we said vector x was the vector xy. Now that we're in R3, it's actually the vector xyz. So just from context, you decide whether this vector x is 2 components or 3 components. Because we're in R3, it's going to have 3 components, x, y, z. So I'm just going to highlight this vector form so that we can see what we're filling into. Vectorization of any point on the line, you could choose the vectorization of p, but you could equally well choose the vectorization of any other point on the line. So just to make that point, I'm going to choose the point q. It can be any point on the line, because what we're then doing is adding all possible multiples along our direction vector. So for that reason, it doesn't matter what your starting point is. Any point, as long as it's on the line, is fine. So we're going to go plus t times our direction vector being -2, -4, -6. So this right here is the vector form for this specific line. And remember that the question is asking us to do 2 things. We want both the vector and the parametric form for this line. So to then get parametric, we're just going to expand. So let's do some details here. We'll work on the right side. First thing we can do, bring the t into the second vector. So -2t, -4t, -6t. Second thing we can do is add the vectors together on the right side. So we'll get things like -2t, -3 minus 4t, and 6 minus 6t. And then very last step is to break this into individual equations, 1 equation for each component. So top one reads x equals -2t, y equals -3 minus 4t, z reads 6 minus 6t. And that's our parametric form. Now let's look at a fact. If someone gives us an equation like ax plus by plus cz equal d, that represents a plane in R3. So we're talking about an infinite flat surface, think something like the xy plane, except it could be tilted in space. So usually when we're talking about these planes, we just represent them as parallelograms like that. So you can imagine we're in 3D. Here are your x, y, z axes. And your plane is this surface here. So it extends infinitely in this direction, infinitely in that direction, but we'll just represent it visually as that parallelogram. So if we were to try to talk about the general or normal form of a line in R3, it would get very messy, because geometrically what a line in R3 is, let's say this is our line in R3, what it is the intersection of 2 planes. So you have to think about, okay, what's one plane that contains that line, and what's a second plane that contains that line, and then let's let those 2 planes intersect. So if you try to represent that in terms of algebra, that would mean that your general or normal form of a line in R3 requires 2 equations. So you'd have to have 2 different equations that represent those 2 different planes, and that just gets extremely messy. So the point is, unhappy face. General or normal form for a line in R3, not nice to work with. So bottom line here is we're just going to use vector or parametric form for lines in R3. If you rephrase that, we're saying don't use general or normal form for lines in R3. So now we can get into our third subtopic, which is the idea of planes in R3. So let's find the normal and general forms of the plane in R3 through the given point and with the given normal. So first, let's just think geometrically here. So we got some plane in space, just draw it like that. And in order to identify this plane, you just need a couple pieces of information. So one, you need to know the normal to the plane. So the normal being a vector that's perpendicular to the plane, that gives you a sense of how your plane is tilting in space. But once you know that normal vector, you still haven't completely identified that plane yet because you don't know how far up or down along that normal vector the plane could be. See, it could be like sitting here and being perpendicular to that normal vector. It could be further down. So what you then need is just one point anywhere on that plane to identify where that plane is, just so that we know how far up or down it is. Otherwise, the plane could be, say, down here and still perpendicular to that same vector. So you can see we've got these two pieces of information in the question, and so that should be enough to identify our plane. So let's start with the normal form, and then we can move into general from there. So normal form is going to look familiar. It's the same as the normal form for a line. We just go n.x equals n.p, and we'll fill in the details. So our normal vector is 1, 1, 2. That's getting dotted with vector x. Vector x just is a vector of variables. For in 3D, it's vector x, y, z. And we're saying that's equal to 1, 1, 2 dotted with, now vector p just represents the vectorization of any point that's on your plane. So in this case, we were given the point 1, -1, 3. It does not matter how you choose this point, you will still end up with the correct normal form, as long as your point is on your object. Okay, so that's the answer we're looking for there for normal form. And then if we expand this, then we get the general form. So expand the dot product on the left, we'd have x plus y plus 2z. Expand the dot product on the right, we'd have 6. So it's quick to move between these two forms. You move down into general form just by expanding. And if you had general form and you wanted to go into normal form, remember the normal vector just comes from the coefficients. So we can look at this general form here and we can say, oh, the normal vector is 1, 1, 2. So that would help us build the left side. And then you just choose any point that lies on this plane. And to get the right side here, you take your normal vector and just dot it with the vectorization of that point. So quite quick to move between general and normal form. So last idea that we need here then is the idea of vector form of a plane in R3. So that's going to look like vector x equals vector p plus s times vector u plus t times vector v, where u and v are non-parallel direction vectors, and s and t are any real numbers. So let's try to understand just from a geometric point of view why this highlighted equation here really describes a plane. So imagine you've got some plane in space, tilted in space. So if you could find one point, let's call it P, one point that lies on that plane, and then you could describe a couple of directions that lie on that plane. Let's say, you can travel along vector u and stay on the plane. You can travel along, let's say, vector v and stay on the plane. Let's think about what this highlighted equation is describing. So this vector x here just represents a point on the plane. And so it's saying to get a point on the plane, you can start at point P, and you can travel any multiple you like along u, and you can also travel any multiple you like along v. S and t just representing any real numbers. So if you let both s and t be 0, you would just be sitting at P. If you let s vary, then that's like saying, okay, I can travel any multiple I like along U, forwards and backwards, so that traces out that direction. If you let t vary, you're saying, okay, I can travel from P any multiple along V that I like, including forwards and backwards. And you can also take sums of these things. So you could start at P. You could travel, say, 2 units along U to get here, and then travel some multiple along V to get to this point here. So as you take all these different multiples of U and V, what you're doing is you really are tracing out every point on this plane. So let's practice vector and parametric form for a plane. So let's find the vector and parametric form of the plane through 3 points. So we'll just draw a picture here. So we've got some plane, and we know 3 points, let's say P, Q, R, are positioned like that. Doesn't really matter how we position them in this diagram. And so the idea is that if you consider P to be your starting point, you can use the other 2 points to construct direction vectors for this plane. So you can say that's going to be vector U, that's going to be vector V. And it's important that these 2 vectors are not parallel. So as long as U and V are non-parallel, then you really will be describing a plane. Whereas in this strange case that we have on the right side, our vectors U and V are parallel. And when you write down an equation like vector x equals vector P plus s times U plus t times V, you'd only really be tracing out a line. So that's why in the definition of the vector form, we have to be careful to say that U and V are non-parallel. So let's build our 2 direction vectors. We'll say vector U is the vector that runs from P to Q. So we'll think Q minus P, that would give us -6, 6, 0. And our second direction vector, vector V, let's say is P, the vector that goes from P to R. So we'll think R minus P gives us -6, 0, 3. Okay, and there's no reason that you have to specifically do it this way. So someone else might set this up differently and say, okay, here are my points P, Q, R, and they might say, okay, I want U to be this vector and I want V to be that vector. That's totally fine as well. So our answers are not unique, but we will at the end of the day be describing the same plane. So now let's write down our vector form. So the equation is going to look like vector x equals vector P plus s times vector U plus t times vector V. X is just our vector of variables. It's x, y, z since we're in R3. Vector P is the vectorization of any point on the plane. So I would say it would be natural to choose the point P and write 6, 0, 0 here. But if you wanted to vectorize Q or vectorize R, that's totally fine because this just represents any point that's on that plane. And then we write plus s times our first direction vector, -6, 6, 0, plus t times our second direction vector, which was -6, 0, 3. So that's half the answer right there. That's the vector form for this particular plane. And if we expand this out, then we're going to get parametric form. So let's do the algebra. We're going to work on expanding the right side. So let's multiply the s through. -6s, 6s, 0. Multiply the t through, -6t, 0, 3t. Okay, and then maybe a couple more steps of algebra. On the right side now we're adding these vectors together. So in the first component you'd have 6 minus 6s minus 6t. Second component 6s, and third component 3t. So now here is our parametric form coming up. Parametric form consists of one equation for each component. So x is 6 minus 6s minus 6t. Y is 6s, and that's our parametric form. So that's the other half of our answer. So now we can do a big summary of everything we've said so far. I would point out that there are 3 types of objects that we have described. We did the line in R2, then we did the line in R3, and then we did the plane in R3. And for each of those 3 objects, there are potentially 4 different forms. 4 different ways of writing down that object. So I would think about just drawing a line here because the general and normal form quite closely related, and the vector and parametric form also quite closely related. Okay, so let's think about a line in R2. General form is ax plus by equals c. Normal form is if you re-express that using the dot product. So you write n dot x equals n dot p, where n is your normal vector. Okay, and then vector form is a more geometric form of describing a line. You write vector x equals vector p plus t times vector d, where d is your direction vector for the line. And if you expand that out, you can turn that into parametric form. So vector and parametric form quite closely related. Okay, now let's jump over to lines in R3. If you're talking about the vector form of a line in R3, it's really the exact same equation. The only difference is that these vectors are going to have 3 components instead of 2. So I would make a connection here and say, okay, vector form for a line, it's really the same equation, whether we're in R2 or R3, just a different number of components. And when you write out your parametric form, then you would have 3 different equations. For lines in R3, we don't talk about general or normal form because really a line in R3 is the intersection of 2 different planes. So this general form would get very messy because you'd really need 2 different equations there to describe that line. So we just don't deal with that messy case. Okay, and then let's jump over to planes in R3. If you wanted the general form for a plane, it's just an equation where you write all your variables on the left side. So ax plus by plus cz equal d. And you could re-express that in normal form just by bringing the normal vector into the discussion. So the normal vector being the vector that's perpendicular to that plane. You could rewrite this as n dot x equals n dot p. So the connection I would make here is that normal form for a line in R2 looks very similar to normal form for a plane in R3. The only difference is that if you're in R3, the vectors will have 3 components. So I would make a connection this way. Okay, and then let's talk about vector and parametric form for a plane in R3. So your vector form says vector x equals vector p plus s times u plus t times v, meaning to get any point on your plane, start at some point on your plane, any point, travel any distance you like along your first direction vector, and travel any distance you like along your second direction vector. And if you were to actually expand out this equation and break it up into components, then you would have parametric form. So the whole point of doing these different forms is that different forms are useful for different problems. So what we're going to do now is look at the geometry problems that we can solve, given that we've now got good ways of expressing lines and planes. So here's a geometry problem for us. We want to find the distance between the point B and the plane, which we'll call P. So imagine we've got this plane in R3, and presumably this point B does not lie on the plane. Otherwise, it's not a very interesting question. If you want to confirm that B is not on the plane, just check if 133 satisfies this equation. No, it does not. So that tells us that that point B is not on that plane. Okay, now when we talk about distance between a point and a plane, we're always talking shortest distance. In fact, anywhere in the course when we say distance, we mean shortest distance. And what that means is the distance in the direction that's perpendicular to P. So you're trying to measure this dotted line distance here. So imagine P, it's not necessarily sitting exactly horizontally in space, could be slightly tilted. So let's say the direction that's perpendicular to P is this direction here. Remember, the normal vector is a vector that gives us a direction that's perpendicular. So we would want to travel from the plane in a direction that's parallel to our normal vector up to B. So here's how we're going to solve the problem geometrically. We're going to start by choosing any point on the plane. Does not matter how we choose that point, and we'll call that A. So we can build a vector that's going from A to B, and that almost certainly will not be going parallel to our normal vector. We've got a normal vector that's going perpendicular to our plane, and we'll be able to build this red vector here using a projection. So this red vector is going to be the projection onto n of our vector AB, and the length of this red vector is what we're looking for. So the distance is going to be the length of the projection onto n of AB. So usually when I'm trying to solve a geometry problem like this, I'll reason through it geometrically first. And now that's going to motivate us to do some calculations. All right, so here's how the calculation part works. So A is going to be any point on the plane. So let's look at the equation for our plane. This is given to us in general form. And let's just choose a point that satisfies this. So what you can do is set two of your variables equal to 0. Let's say you set y and z equal to 0. That would force x to equal 7 in order to satisfy that equation. So we're just looking for a combination of x, y, z values that satisfy that equation. Great, and then from there, we're going to build the vector AB. So to get AB, let's think B minus A. So here's our point B here. It was given as 1, 3, 3. We know A is 7, 0, 0. So if we go B minus A, negative 6, 3, 3. Great. The next thing we need is our normal vector. And let's think back to how general and normal form are related. Remember that if you have the general form of a plane in R3, you can pick out the normal vector just by grabbing the coefficients. So we can automatically say the normal vector is going to be 1, 1, 2. So now we're able to calculate the projection onto n of AB. So let's think back to our projection formula. We need to do the dot product of n with AB, and everything else is about what we're projecting onto. So it's divided by length squared of n in the direction n. All right, so doing our dot product gives us 3. Length squared of n, so just go through and square each of the components, sum those up, that's 6. And we're going in the direction of n. Okay, now it might be easier to simplify this. Let's just call that 1/2, 1, 1, 2. And then as we said at the beginning of the problem, the way we're going to get our distance is by taking the length of this vector. Okay, remember from way back when we said that if you're ever trying to take the length of a constant times a vector, you can bring that constant out in front. Just remember you need to take the absolute value of it. So technically we should say absolute value of 1/2 times the length of 1, 1, 2. But because 1/2 is a positive number, it's okay to say 1/2. You would just have to be a little bit careful if you were bringing a negative constant out. Okay, so our length of the vector 1, 1, 2 is √6. Therefore, our answer is √6/2. That gives us our distance between our point and the plane. So that's a really useful applied problem to be able to solve. And we needed the concept of a normal vector in general form in order to work our way through that problem. Now let's find the distance between the point and some line in R3. So let's try to draw a picture. Let's talk about this line L here first. So we know we've got some line L that contains the point A, and we also understand the direction vector for that line. And then we've got some point B, which presumably is not on the line. So let's say B, just for the sake of our picture, let's say B is over here. So when we say distance, we're talking about the shortest distance, meaning the distance in the direction that's perpendicular to our line. So we're looking for this dotted red distance here. Now we've got a line in R3, and the thing to be aware of is that a line in R3 does not have a normal vector. Let's talk geometry for a second. So we're in space, you've got a line. This line has an entire plane that's perpendicular to it. So there are really two different directions here, two different direction vectors that would both be perpendicular to that line. So we have to be careful not to fall into the trap of talking about the normal vector to this line, because there isn't one. What we can do is we can build a vector going from A to B. We know how to do that because we're given point A and B in the question. We could project this vector onto the direction vector for the line. So imagine doing this projection. So this heavy red vector here that we've drawn is the projection onto the direction vector of AB. So that would be also relatively easy to calculate because we were given our direction vector in the question. And then we could build this vector here by thinking about a subtraction. So this new red vector, that would have to be AB minus the projection onto D of AB. So I just think about the fact that if I add this and this, we're supposed to be making AB. So this guy would have to be AB minus the projection. If you don't want to do that mentally, you could just call this temporarily, you could call it question mark, and you could say projection onto D of AB plus question mark is supposed to build the vector AB, and then you could solve for question mark, and you could say, yeah, that would be AB minus the projection onto D of AB, if you wanted really a step-by-step approach to figuring that out. So now the distance that we're looking for, being the distance between the point B and this line here, is going to be the length of that vector AB minus the projection onto D of AB. Well, in terms of the calculation, first couple things I would calculate. Let's think about building the vector from A to B. So think B minus A. We can see our points A and B in the question. So B minus A, 1, 0, negative 2. And the direction vector D was given to us in the question. So I'll just copy that down, and that way we don't need to keep looking back at the question. So let's calculate the projection onto D of AB. We are going to dot D with AB, and everything else is about what we're projecting onto. So dividing by length squared of D, and then in the direction of D. That's minus 1/2 in the direction of D. Okay, and then next thing we need to do is calculate AB minus the projection onto D of AB. So we're going to go 1, 0, negative 2, subtracting off something that has a negative coefficient, so plus 1/2, 1, 0, 1. And if we do the algebra here, we'll get things like 1 plus 1/2, so let's call it 3/2. Middle component is 0, and then bottom component negative 2 plus 1/2 gives us minus 3/2. Okay, now we are going to want to calculate the length of this vector. And it's better to do that when you don't have fractions in the vector. So let's pull the half out in front and say that's half of 3, 0, negative 3. So the distance that we're looking for is the length of this vector, half of 3, 0, negative 3. We can pull the half out in front as long as we're aware that in general we should be taking the absolute value of that constant. Absolute value of a half is a half, and then multiply that by the length of 3, 0, negative 3. So the length of 3, 0, negative 3, root 18. So our answer is going to be root 18 over 2. Or you could simplify that. You could say that's 3 root 2 over 2 if you wanted. In the course pack, you may see a question about distance between parallel planes. So imagine that you've got two planes here, parallel to one another. You want to try to find the distance between them. What you can do, choose any point on either of the planes to be your point B. So let's just say this is a point. Forget about this bottom plane now and just consider it to be a question about what is the distance between the point B and the top plane. And then that turns it into a problem that we already know how to solve. Similarly, if you wanted the distance between parallel lines, let's say you were given these two lines here, choose any point on either line to be your point B. So let's say this is our point B. So we're now going to forget about the second line, and we're now just phrasing it as what's the distance between the first line and the point B. And that's the problem that we just solved. So we know how to solve that one as well. So while we're on this topic of lines and planes, we can also talk about the angle between two planes. And we will define the angle between two planes to be the angle between their normal vectors. So let's just draw a picture. Let's imagine that you've got this plane here, the red plane, and this plane here, the blue plane. And so if we want to talk about at what angle these planes are meeting, the simplest way to do that is to think about the normal vectors for your two planes. So you could say, well, the red plane has this normal vector here, n1, and the blue plane has this normal vector here, n2. And remember that vectors can be shifted around, so I can reposition this. So vector n1 is going like this. Let's just position the two vectors tail to tail. Vector n2 can be shifted like that, and then we can talk about the angle between these two vectors. So the angle between the normals is what describes the angle at which these planes are meeting. So two planes are considered to be parallel planes if they have parallel normals, and two planes are considered to be orthogonal if their normals are orthogonal. So if someone gives you the equation of two planes and they want to say, are these parallel? Just figure out the normal vectors and figure out whether those vectors are multiples of one another. So you'd have a situation where n1 is equal to some multiple times n2. If you want to figure out whether your planes are orthogonal, check whether your normal vectors are orthogonal. So you're really asking, do n1 and n2 have dot product 0? If that's true, then your planes are orthogonal. So we've seen 4 ways of describing lines and planes. The 4 forms are general, normal, vector, and parametric. We've seen that different forms are useful for different geometry problems. And our ultimate goal with this is to solve geometry problems like finding distances and finding angles between objects. Thanks for watching.